much anything if we want, yes.
Doesn't the cost go up as well?
Does the cost of reverse engineering go up?
Doesn't the cost go up as the chips get smaller? Doesn't it cost you more to reverse engineer?
Oh yes, yeah. So a focused ion beam you won't get below $300,000, whereas the microscope we're using now is about $1,000. Yeah. So it will definitely cost more to reverse engineer. But if you find a bug in a Pentium 4, I'm not sure how much that is worth anyway. Yeah. So it might be worth the 300,000 investment in the FIP right there.
I have a question. Could you implement public key cryptography in hardware?
Oh, sure, yeah, and people have.
Well, if you have a signature function and keep your private key private and not in the door opener, it would be able to make it more secure. Do you think that's an option?
Yes, well, it very much depends on your scenario, whether or not public key crypto is an option. So often what you want to prevent is that a device is being copied. If you want to prevent a device from being copied, you still have, even with public key crypto, you'll have to store some portion of the key on the chip that you need to hide from the attacker. And from what we can tell, these hardware devices are just not capable of keeping anything secret. That would be one short answer. But there are applications where public key would at least increase the security a lot, yes.
Manufacturers tend to use glue logic in their newest chips. Doesn't that make detection of logical gates much more complicated because they are not recognizable that easy anymore?
I haven't seen a chip that wouldn't have been assembled from a standard cell library. I think glue logic is really just used to fill gaps, from what I understand. Rather than building the entire chip from it. So we could take our approach one step further, where we don't say we need to first categorize logic cells into functions and then find these functions across the chip. We could, one by one, reverse engineer the functions themselves automated. We didn't need to do that yet because everything that we see is standard cell libraries, but it's just one more step in the reverse engineering. It doesn't make it very much more difficult.
Sorry, just now you're saying the automated tracing. The automated tracing that you mentioned. Just now one of the slides.
You want me to go back some slides?
Yeah, the automated tracing.
Automated tracing, yeah, hold on. Here we go.
So you have a software that helps you to trace out all the traces.
Exactly, and this is a very old screenshot. You'll see that it actually made some errors. This dot, for example, wasn't recognized. Same here, same here. We have much better accuracy today, from what I understand. Yes, so we have accuracy close to what we need in our results, and then a few errors that are being made, they're easy to spot. But this is all automated, yes.
Then the software that is being used, what is the name again?
What is the name?
Yeah.
It's not released yet, but it will. Nitram from the CCC in Berlin will release his software in January, hopefully, fingers crossed. And then the name is DGETA, DEGETA.
Just a quick question. When you've actually done all this reverse engineering, you will have the working description of the chip in machine-readable form. Have you considered trying to simulate the chip based on this information to judge whether or not the chip behaves like your real chip does?
Yes. In fact, my answer just a minute ago, that we could automatically reverse engineering the different logic cells, that would require simulation of each logic cell. So we can simulate parts of it or even the entire chip, but it gets extremely slow. Simulating hardware in software is not efficient, and we have so far only reverse engineered cryptography, where it was very clear when we found the right function, and we didn't actually have to simulate it. But you can, in fact, if you just have the chip images, if you have very high quality chip images, you can use those as the input into a hardware simulation tool, and it will very precisely simulate it. Yeah.
What sort of topology space are you using?
What polishing paste are we using? 0.0 for micrometer, graining size. Is it diamond based? Silicon based. Thanks, Starbuck. Yeah, you can probably take pretty much anything you want as long as it's not too grossly grained, so you cut your chip.
Is it really as simple as you say to reconstruct the wires? Because as far as I know, there are at least like 5 to 7 metal layers to interconnect the condensators there.
That can be. I think the record is around 13, so anywhere between 1 and 13 metal layers. But once you have the process automated, it's easy to work with more than just a few layers. Fortunately, the chips we have been looking at, they're kind of older because they implement proprietary encryption, which has been known to not be a good idea for a while. They have had at most 4 metal layers. So the layers, they do have dedicated functions, though. It's not that most connections of a short distance would go across all these layers. They would usually come in bundles and go longer distances if they're on higher levels. So the higher levels don't add much complexity. Most complexity is always found on the lower levels. More questions?
Can you distinguish P and N transistors just by looking at the photo?
The question is, can we distinguish P and N transistors just by looking from the photos? And the answer is yes and no. So these transistors, let's look at this. These transistors, one is an N and one is a P. They look almost exactly the same, only notice that this one is bigger. The PMOS is always bigger. Depending on the configuration, that's not always true. If you had, say, 3 NAND, then the NMOSes would actually be larger. But because you know it's a 3 NAND, you expect that, and you can still tell which is which. Plus, they're always nicely separated. So P is always on top, and N is always below.
I'm wondering, actually, there are very small structures, and if you're going there on an angle, is there a problem that you might actually see several layers at once, so that you see layer 2 and 3, or something like that?
That is a problem in the polishing, yes. So if you are not super careful in the polishing, you will see this is the silicon substrate. Here are the transistors, and up here, that's the logic layer function. So the cut was diagonal through the chip, and you did damage several layers here at the same time. The goal is always to be as planar as possible to the backside of the chip, so that you only ever see one layer at a time. If you don't get that perfectly fine, that's cool too, because once you have enough pictures from one layer, and then maybe across different cuts, you can still reassemble it. So you don't, in your first cut, have to get everything down to one layer. You can, with your next chip, try again, and eventually you'll have full coverage of each layer. Does that make sense? Cool.
Have you seen any nice chip art?
Say it again?
Have you seen any chip art?
You haven't seen any what?
Chip art.
Oh, chip art. No, well, I'm not an artist. And would you call yourself an artist? Maybe a little bit? Okay. No. But, yeah, we'd love to help anybody who wants to pick it up.
What's the structural wise of this chip, the technology?
It's like 380 nano, I think. So it's fairly old, yeah.
Okay, thanks.
Have you ever tried to reverse any non-planar technology, like MEMS?
Yes, and in fact, this is a non-planar chip. Can't really tell in these images. They happen to be fairly nice, but so planarizing a chip means that after you put a layer down, you basically file it so it's straight again, and then you put the next layer down and you file it again. Before they started doing that, the chips became on top of the lines a little wobbly. And if we file these down, we actually see that wherever there's a line below, we have to file harder, kind of, or something is left if we file with the same strength everywhere. So non-planarized chips are harder to work with, but they're also easier because they're old and everything is bigger and it's easier to take pictures of. But yeah, we can break both. Cool.
Have you come across any chips with physically unclonable functions?
Interesting. Yeah, I'm working with one right now, and the idea of a physically unclonable function is ingenious, but the execution I've seen so far is definitely breakable. So a physically unclonable function works off the principle that the key to a cryptographic function is generated by different chips just naturally being different. Like humans are always different, even if they are twins. And so you build two chips, and where the process variation makes them different enough so they're cryptographically distinguishable. And the idea is to make them to make the differences so small that nobody who probes into the chip can find the differences, because you already broke it in the process of probing in. Which in theory would work, only the puffs that I've seen do not adhere to cryptographic principles. So you can break them without even reverse engineering what they're doing from the outside. Okay, are we all good? There's one more question in the back. There's two more, so two more questions, and then we'll all have dinner.
Hello. So what would you do to secure the chip?
Good question. Let me cite Kristanovsky here, who has been breaking microchips for at least 15 years. He says everything helps, but nothing is perfect. So try to be moving target, try to have as much different security types in your chip as possible, and keep replacing them. There's this company NDS, they make satellite smart cards and sell them kind of expensively. Every batch of their chips, from what I understand, is somewhat different from the batch before. So without being broken into, they never manufacture many chips of the same type and just keep moving, so nobody has a huge incentive to break them, because you can only ever break a small number of chips. That's probably the best advice I can give, but nothing is perfect. Okay, the question in the back?
Yeah, I think there's a high degree of automation in your image analysis. Have you considered increasing the acquisition maybe with CNC
Yeah, so the question is, have we automated any part of the acquisition of the images? And sure, taking the images doesn't take all that long. Taking all the different images with a stage that automatically moves, which we're already using sometimes, takes maybe 5 minutes. So the polishing will be a bottleneck, the getting just right to the right layer where you want to be. Yeah, and I'm not sure how much you can automate that. If you could maybe build a robot that puts it in HF for 30 seconds and then takes images and then does that. Yeah, we haven't automated that yet, no. Okay, well, this has been fun. Thanks a lot for all the questions, and have a good evening.